Predators and prey continuously adapt to each other. They might run faster, evolve stronger protection, or more acute senses. Now, this type of coevolution is commonly called an arms race, and echolocating bats and their insect prey are prime examples of such a coevolutionary arms race. Before the bats, night-flying insects likely lived relatively carefree lives, experiencing little predation, and as such they were a large unexploited niche of food. Now, the bats clearly struck first in this arms race through the combined evolution of flight and echolocation, allowing them to hunt these night-flying insects. But insects rapidly caught on, and many of them evolved bat-detecting ears, allowing them to hear and evade the bats. Now, it wouldn't be much of an arms race if the parties involved only struck once, and indeed there are numerous examples of how insects escalated their defenses. However, proper countermeasures from the bats are very rare. Some 15 years ago, the quiet Barbastelle bat was presented as the prime example of how bats outsmarted the hearing of their prey. Typically, the echolocation calls of bats that hunt insects in the open air are extremely loud as a jackhammer. And such loud calls are needed for the bats to detect their prey over sufficiently long distances because the tiny insects they hunt reflect only weak echoes and ultrasound attenuates quickly in air. In contrast, the calls of the Barbastelle bat are 10 to 20 times quieter than those of other bats hunting in the air. This tremendously reduces their detection distance for prey, like us using a dim candle instead of a bright torch at night. However, because of these faint calls, eared insects cannot hear the attacking Barbastelles, allowing the bats to sneak up and catch them. For years we thought that this stealth echolocation evolved as a countermeasure to outsmart the hearing of insects, because we could not envision any other benefit of such quiet calls. In this study, however, we showed that this evolutionary scenario is wrong. When we examine the close relatives of the Barbastelle bats, the plecotines, like this brown long-eared bat, they stand out by hunting by gleaning. That is, they pluck insects from surfaces instead of catching them in midair. Such bats are very quiet because this greatly reduces the amount of unwanted echoes they receive when they fly around trees, bushes, or the ground searching for food. Given that most of the Barbastelle's relatives are gleaners, we hypothesized that their ancestor was likely a gleaner too. Indeed, using ancestral state reconstruction, we find that the properties of their common ancestor fit to those of a quiet gleaner. In addition, we tested the echolocation of free-flying Barbastelles and compared to other bat species that hunt in similar habitats. And we find that Barbastelles use different call timing and call frequency during prey capture, and they do not emit loud calls, even when we challenge them by exposing them to loud background noise. All this indicates that today's Barbastelles are limited in their call emission, particularly in how loud they can call. So where is this limitation coming from? Unlike most open-air foragers, the Barbastelle bat and its plecotine relatives emit their calls through the nose instead of the mouth. Because nostrils have a smaller and fixed size compared to a flexible mouth, this likely limits both the frequency range and the maximum intensity of their calls. So the reason why the Barbastelles are so quiet today is not the result of an evolutionary arms race between bats and insects, but simply because they descend from quiet nose-emitting bats that cannot call as loudly as others. Yet because of this quiet echolocation, they also had access to unsuspecting eared insects flying in the open. This combination allowed over evolutionary time for the transition from a gleaning ancestor to the aerial hunting quiet Barbastelles that we know today.